What mass of solid potassium fluoride is required to make 5.0 liters of a pH 8.35 solution? In solution, here's what happens to potassium fluoride. We get 100% dissociation. The potassium ion does nothing to affect pH because, as we've said before, what I call strong anions or strong cations don't affect pH. But the fluoride ion does affect pH, and it does it in this way. It's going to accept a proton from water, forming HF, hydrofluoric acid, which is a weak acid, and the hydroxide ion, which is a rather strongly basic species. Let's skip a little bit of space if you are writing any of this down, because we're going to put some ice calculations in here right below the equation. So skip a little bit of space, but if the pH up here at the top of the screen is 8.35, then we can see down here at the bottom that the pOH must be 5.65, because the sum of those two must equal 14, which means we can find the OH ion concentration by taking 10 to the negative 5.65. That turns out to be 2.24 times 10 to the negative 6th molar. That is the hydroxide ion concentration at equilibrium. And whenever we are doing an ice calculation, it is the at equilibrium number that we are interested in most. So, we know the OH ion concentration at equilibrium. Furthermore, we know the HF concentration at equilibrium. The water concentration is irrelevant. The fluoride ion, we don't know what it started out as, but we do know that it went down by 2.24 times 10 to the negative 6th. This is where we stand so far. How is this going to help us? Well, eventually, if we're able to calculate X, that is the initial concentration of fluoride ion, which means that relates to the initial mass of the salt that we dumped into this solution in the first place. At this point, we need the Kb for the fluoride ion. This isn't always found in references, but the Ka for hydrofluoric acid always is. And if we were to look that up, or Google it, you would get a number somewhere around 6.8 times 10 to the negative 4th for the Ka for hydrofluoric acid. But look at our equation. It's right in the middle of the screen here. It starts with F minus. You can see that F minus is not acting as an acid, it's acting as a base. So we need the Kb for F minus, which was related to the Ka for HF, in that the product of those two is 1 times 10 to the negative 14th. So we look up the Ka for hydrofluoric acid, and then we, from that, calculate the Kb for the fluoride ion, which is what we need, 1.5 times 10 to the negative 11th. Don't rewrite any of this. I've just recopied what came from the previous slide that is relevant to this slide. We're now going to write our equilibrium constant expression, products over reactants, leaving out water. We calculated the Kb. You might remember at the bottom of the last slide we calculated Kb to be 1.5 times 10 to the negative 11th. That's going to be equal to this expression here, products over reactants, right from our at equilibrium line in our ice calculation. We can solve that for X. It's a little bit of work, but it can be done. If you do, you get this number, 0.334 molar. That is the initial concentration of the fluoride ion, which, because we have 100% dissociation, that was also the initial concentration of the potassium fluoride. Now, what we need is what mass of potassium fluoride was dumped in. We know the molarity of the potassium fluoride when we dumped it in to the solution. We know that we have, in the denominator, 5 liters of solution. So from that, we can determine the moles of potassium fluoride that we needed to dump in. And of course, from here, it's child's play to turn this into grams. We use the molar mass of Kf, which we find with the help of the periodic table, and we find that we need to add 97 grams of potassium fluoride to 5 liters of solution to give us our pH of 8.35.